Quark Model 1964. But the very success of the Eightfold Way begs the question, why do hadrons fit into these curious patterns? The periodic table had to wait many years for quantum mechanics and the Pauli exclusion principle to provide its explanation. An understanding of the Eightfold Way, however, came already in 1964 when Gell-Mann and Zweig independently proposed that all hadrons are in fact composed of even more elementary constituents, which Gell-Mann called quarks. The quarks come in three types or flavors, forming a triangular eightfold way pattern. The quarks: S equals 0 for D and U, S equals -1 for S. The U for up quark carries a charge of 2/3 and a strangeness of 0. The D down quark carries a charge of -1/3 and S equals 0. The S, originally sideways but now more commonly strange quark, has Q equal -1/3 and S equal -1. To each quark Q, there corresponds an antiquark Q bar with the opposite charge and strangeness. The antiquarks: S equals 1 for S bar, S equals 0 for U bar and D bar. The Quark model asserts that Number 1. Every baryon is composed of 3 quarks and every antibaryon is composed of 3 antiquarks. Number 2. Every meson is composed of a quark and an antiquark. With these two rules, it is matter of elementary arithmetic to construct the baryon decuplet and the meson octet. All we need to do is list the combinations of 3 quarks or quark-antiquark pairs and add up their charge and strangeness. The baryon decuplet: 3 up quark, charge 2, strangeness 0, delta ++. 2 up quark, 1 down quark, charge 1, strangeness 0, delta +. 1 up quark, 2 down quark, charge 0, strangeness 0, delta 0. 3 down quark, charge -1, strangeness 0, delta -. 2 up quark, 1 strange quark, charge 1, strangeness -1, sigma star plus. 1 up quark, 1 down quark, 1 strange quark, charge 0, strangeness -1, sigma star 0. 2 down quark, 1 strange quark, charge -1, strangeness -1, sigma star minus. 1 up quark, 2 strange quark, charge 0, strangeness -2, xi star 0. 1 down quark, 2 strange quark, charge -1, strangeness -2, xi star minus. 3 strange quark, charge -1, strangeness -3, omega minus. Notice that there are 10 combinations of 3 quarks. 3 U's, for instance, at Q equal to 2/3 each, yield a total charge of +2 and a strangeness of 0. This is the delta ++ particle. Continuing down the table, we find all the members of the decuplet ending with the omega minus, which is evidently made of 3 s quarks. A similar enumeration of the quark-antiquark combinations yields the meson table, the meson nonet. U bar, charge 0, strangeness 0, pi 0. U D bar, charge 1, strangeness 0, pi positive. D U bar, charge -1, strangeness 0, pi minus. D bar, charge 0, strangeness 0, eta. U is bar, charge 1, strangeness 1, K positive. D is bar, charge 0, strangeness 1, K 0. S U bar, charge minus 1, strangeness minus 1, K minus. S D bar, charge 0, strangeness minus 1, K 0 bar. S S bar, charge 0, strangeness 0, question mark. But wait, there are 9 combinations here and only 8 particles in the meson nonet. The quark model requires that there be a third meson in addition to the pi 0 and the eta, with Q equals 0 and S equals 0. As it turns out, just such a particle had already been found experimentally, the eta prime. In the eightfold way, the eta prime had been classified as a singlet, all by itself. According to the quark model, it properly belongs with the other 8 mesons to form a meson nonet. Actually, since U bar, D bar and S bar all have Q equals 0 and S equals 0, it is not possible to say on the basis of anything we have done so far which is the pi 0, which the eta and which the eta prime. But never mind, the point is that there are 3 mesons with Q equal S equal 0. By the way, the anti-mesons automatically fall in the same supermultiplet as the mesons. UD bar is the antiparticle of DU bar and vice versa. You may have noticed that I avoided talking about the baryon octet, and it is far from obvious how we are going to get 8 baryons by putting together 3 quarks. In truth, the procedure is perfectly straightforward, but it does call for some facility in handling spins, and I would rather save it until chapter 5. For now, I'll just tantalize you with the mysterious observation that if you take the decouplet and knock off the 3 corners where the quarks are identical, UUU, DDD and SSS, and double the center where all 3 are different, UDS, you obtain precisely the 8 states in the baryon octet. So the same set of quarks can account for the octet. It's just that some combinations do not appear at all and one appears twice. Indeed, all the eightfold way supermultiplets emerge in a natural way from the quark model. Of course, the same combination of quarks can go to make a number of different particles. The delta plus and the proton are both composed of 2 U's and a D. The pi plus and the rho plus are both UD bar, and so on. Just as the hydrogen atom, electron plus proton, has many different energy levels, so a given collection of quarks can bind together in many different ways. But whereas the various energy levels in the electron-proton system are relatively close together, the spacings are typically severe electron volts in an atom whose rest energy is nearly 10 to the power 9 electron volts, so that we naturally think of them all as hydrogen. The energy spacings for different states of a bound quark system are very large, and we normally regard them as distinct particles. Thus, we can in principle construct an infinite number of hadrons out of only 3 quarks. Notice, however, that some things are absolutely excluded in the quark model. For example, a baryon with S equals 0 and Q equal -2. No combination of the 3 quarks can produce these numbers. Nor can there be a meson with a charge of +2 like the delta ++ baryon, or a strangeness of -3 like the omega-. For a long time, there were major experimental searches for these so-called exotic particles. Their discovery would be devastating for the Quark model, but none has ever been found. See problem 1.11. The Quark model does, however, suffer from one profound embarrassment. In spite of the most diligent search over a period of 20 years, no one has ever seen an individual quark. Now, if a proton is really made out of 3 quarks, you'd think that if you hit one hard enough, the quarks ought to come popping out. Nor would they be hard to recognize, carrying as they do the conspicuous label of fractional charge. An ordinary Millikan oil drop experiment would clinch the identification. Moreover, at least one of the quarks should be absolutely stable. What could it decay into, since there is no lighter particle with fractional charge? So, quarks ought to be easy to produce, easy to identify, and easy to store, and yet no one has ever found one. The failure of experiments to produce isolated quarks occasioned widespread skepticism about the Quark model in the late 60s and early 70s. Those who clung to the model tried to conceal their disappointment by introducing the notion of quark confinement. Perhaps for reasons not yet understood, quarks are absolutely confined within baryons and mesons, so that no matter how hard you try, you cannot get them out. Of course, this doesn't explain anything, it just gives a name to our frustration. But at least it poses sharply what has become a crucial theoretical problem for the 80s: to discover the mechanism responsible for quark confinement. There are some indications that the solution may be at hand. Even if all quarks are stuck inside hadrons, this does not mean they are inaccessible to experimental study. One can probe the inside of a proton in much the same way as Rutherford probed the inside of an atom, by firing something into it. Such experiments were carried out in the late 60s using high-energy electrons at the Stanford Linear Accelerator Center (SLSC). They were repeated in the early 70s using neutrino beams at CERN, and later still using protons. The results of these so-called deep inelastic scattering experiments were strikingly reminiscent of Rutherford's figure 1.12. Most of the incident particles pass right through, whereas a small number bounce back sharply. This means that the charge of the proton is concentrated in small lumps, just as Rutherford's results indicated that the positive charge in an atom is concentrated at the nucleus. Figure 1.12. A. In Rutherford scattering, the number of particles deflected through large angles indicates that the atom has internal structure, a nucleus. B. In deep inelastic scattering, the number of particles deflected through large angles indicates that the proton has internal structures, quarks. The dashed lines show what you would expect if the positive charge were uniformly distributed over the volume of A, the atom, B, the proton. Source: F. Halzen and A. D. Martin, Quarks and Leptons, New York, Wiley, 1984. Copyright John Wiley and Sons. However, in the case of the proton, the evidence suggests 3 lumps. instead of 1. This is strong support for the quark model, obviously, but still not conclusive. Finally, there was a theoretical objection to the quark model. It appears to violate the Pauli exclusion principle. In Pauli's original formulation, the exclusion principle stated that no two electrons can occupy the same state. However, it was later realized that the same rule applies to all particles of half-integer spin. The proof of this is one of the most important achievements of quantum field theory. In particular, the exclusion principle should apply to quarks, which, as we shall see, must carry spin half. Now, the delta++, for instance, is supposed to consist of 3 identical U quarks in the same state. And also the delta minus and the omega minus appeared to be inconsistent with the Pauli principle. In 1964, O.W. Greenberg proposed a way out of this dilemma. He suggested that quarks not only come in 3 flavors, U, D and S, but each of these also comes in 3 colors, red, green and blue, say. To make a baryon, we simply take 1 quark of each color. Then the 3 U's in delta++ are no longer identical. One is red, one's green and one's blue. Since the exclusion principle only applies to identical particles, the problem evaporates. The color hypothesis sounds like sleight of hand, and many people initially considered it the last gasp of Quark model. As it turned out, the introduction of color was one of the most fruitful ideas of our time. I need hardly say that the term color here has absolutely no connection with the ordinary meaning of the word. Redness, blueness and greenness are simply labels used to denote 3 new properties that, in addition to charge and strangeness, the quarks possess. A red quark carries 1 unit of redness, 0 blueness and 0 greenness. Its antiparticle carries -1 unit of redness and so on. We could just as well call these quantities xness, yness and zness, for instance. However, the color terminology has one especially nice feature. It suggests a delightfully simple characterization of the particular quark combinations that are found in nature. All naturally occurring particles are colorless. By colorless, I mean that either the total amount of each color is 0 or all 3 colors are present in equal amounts. The latter case mimics the optical fact that light beams of 3 primary colors combine to make white. This clever rule explains, if that's the word for it, why you can't make a particle out of 2 quarks or 4 quarks, and for that matter, why individual quarks do not occur in nature. The only colorless combinations you can make are QQ bar, the mesons, QQQ, the baryons, and Q bar, Q bar, Q bar, the antibaryons. You could have 6 quarks, of course, but we would interpret that as a bound state of 2 baryons.